Hi Lily, we're looking at reciprocal functions today. I'm in my staff room and I'm hoping I don't get interrupted, but we'll see how that goes. I also don't have my good microphone that I bought during COVID times, so we'll see how the sound goes as well. All right, so with our reciprocal functions, you've seen the word reciprocal before, and we use the word reciprocal in junior school when we're talking about fractions. And we say when we're dividing by a fraction, we multiply by the reciprocal. And you learnt that a reciprocal fraction was when we had a fraction and we use the word, we turn it upside down. And we're pretty much doing the same sort of thing, but with functions. So when we take the reciprocal of a fraction, say our fraction was 3/4, the reciprocal of that fraction, and I'm not going to use the equal sign because they're not equal, the reciprocal of 3/4 is 1/3/4, which is 4/3, which is why we kind of say, it's the fraction's upside down. So instead of reciprocal fractions, we're looking at reciprocal functions. And the main one we look at is the hyperbola. So when we're dealing with hyperbolas and other reciprocal functions, we end up with things called asymptotes. And asymptotes happen where the original function, that's f of x, equals 0. Because we have this rule that we can't divide by 0, so if we've got 1 divided by f of x, where f of x is 0, we end up with asymptotes. So we have vertical asymptotes where f of x equals 0, and also horizontal asymptotes where y equals 0, because there is no number that I can substitute for f of x which will result in 0. 1 divided by, and there's nothing that will give me 0. So for that reason, we've got multiple asymptotes happening with reciprocal functions. All right, let's have a look at this example. So our f of x is a parabola, which we could probably sketch pretty easily. And I'm going to actually sketch the parabola as well as the reciprocal of the parabola. We're also asked to find the domain and range. Now, the parabola, being a polynomial, has a domain of all real x. It being a even degreed polynomial, it will have either a maximum or a minimum, in this case a minimum. However, all sorts of crazy things are going to happen. This particular parabola will have x-intercepts, which means it will have some asymptotes. So if we have a look at f of x first, because I want to sketch both, we've got x squared plus 2x minus 3, and I can factorise that as x plus 3, x minus 1, and that tells me that I've got an x-intercept at -3 and an x-intercept at +1. The -3 on the end tells me that's where my y-intercept is. One of the properties of a parabola is it's symmetrical around its axis. Because I know where my two x-intercepts are, I can tell that the axis of symmetry of my parabola is directly in the middle of them. So I'm going to use some of the properties of my parabola . So I've got an extra point because that that dashed line, which isn't part of drawing it, but it just helps me. So there's going to be a minimum turning point at x equals -1. But what I'm going to do to make things easy for myself is draw up a table of values. You would not do that. Your table of values would exist on your calculator. So what you'd do is you'd set up your x values, and once you set those up, you can pretty much keep them as they are. I like, normally if I'm doing it manually, I'll do from -3 to 3 in steps of 1, but I've set up my calculator to have steps of 1/2. But because I can't get the class pad working here quite yet, let me see, what do I want? I want a 3-way table, and I've got to go look it up. That's annoying. There it is. There's my 3-way table. So it's good when I've got 3 values. So my values are going to be x, f of x, and then from that I'll determine 1 on f of x. But what you need to do on your calculator, on the 8200, for your table of values, set up that third column if you wanted to graph both. You're not asked to in this question. I'm just doing it for this first example so that we can see the relationship with what's going on. All right, so I'm going to start with the numbers that I normally do. I already know that -3 is an intercept. I know that -2 will give me -1. 0 will give me -3. 1 will give me 0, and I've just got a few blanks to fill in. So it might be easier substituting that into the factorized version, but you don't have to. Use your calculator. So I'm not doing that at the moment, so I will have 2 times -2, so it's -4 is going to be my minimum turning point, which is pretty much what I expect. This is just a monic parabola, so I kind of know the values. You know, we go up 1, we go up 3, and then I think it would go up to 6 or 7. Let's work it out. That will be 5 times 1 is 5. I don't think the next one will work. Oh, yes, it just does. It just does. 3 plus 3 is 6. 3 minus 1 is 2. 2 times 6 is 12. And then for free, I get the ones that are reflected on the other side. That gives me enough to get a really nice shape for my parabola. So I can see what my f of x looks like. And once again, I'm not asked to sketch this, and you wouldn't sketch something like this in an exam situation unless it was to help you. I'm just doing it for educational purposes. All right, there's some important points on this parabola. That's an important point, and that's an important point because f of x equals 0 at those points. So we're going to have some vertical asymptotes there. So I'm going to switch colours, and I'm going to put in some dotted lines where my vertical asymptotes are going to be. These graphs are frequently in 3 parts. There will be symmetry as well. All right, so for the third line of my table, I will have 1 on f of x. And we can see 1 on 0 is undefined. For -2, my f of x value is negative 3, so I will have minus 1 on 3. I will have minus 1 on 4. I'll have minus 1 on 3. I'll have another undefined value. That's where I've already shown my vertical asymptotes. I will have, now we're getting into some positive values, 1/5, 1/12. So as f of x, that's my original function that I've drawn in that teal colour, as f of x approaches infinity, as it gets bigger, 1 on f of x gets smaller. And the other important number is 1, because 1 divided by 1 is 1. So it's actually where our graphs cross over. So I've got nothing much happening. To start, for negative 2, I have minus 1/3. That's pretty small. For negative 1, I have minus 1/4. That's small, but a little bit closer, and minus 1/3. That's not enough for me. I want to get a better idea of what's happening in between those values, and I don't have enough there. I actually kind of know what it looks like, but that's just me. Let's get some more values. Once again, use your calculator. Don't do it the hard way. So if I've got, I'm going to drill down. I'm going to have a closer look what's happening. I'm pretty confident between negative 2, negative 1 and 1. I'm going to have a look at what's happening between negative 2 and negative 3. So negative 3, I know. And let's make this, let's do it in quarters. So let's make it negative 2 3/4, negative 2 1/2, negative 2 1/4, and negative 2. So let me grab one of my mini calculators. That's the one I want, the FX 8200, because I don't know why I'm doing this manually when I don't have to. All right, I'm going to go to my table, and then I'm going to define my table range as starting at negative 3. I'm going to be ending at 3. Actually, no, I have the remorse for that. I am going to extend that because I don't feel I have any data points. So I might start at negative 5. I know you can't see what I'm doing, but I'll talk you through it anyway. My table range on the 8200 is going to start at negative 5 and it's going to go through to 5. I've got steps of 1/4. Fantastic. I'll run that. Oh, that's very interesting. Okay, let's define my values. My f of x, I'm going to define f of x as x squared plus 2x minus 3. And I'm just having someone come into the staff room. Hopefully it's someone I know. I'll just tell them I'm recording at the moment for a student. Oh, it's Paula. She's going backwards, out backwards. Hi. Paula says hi. All right, so I've entered that. And I'm going to define my g of x. I wonder if I can define it as 1 divided by f of x. I can define it as 1 divided by f of x. That's handy. That's very handy indeed. So I have tried to set up my table because I was interested to see what my calculator would do if it can't find a value. And it spits the dummy. That's very interesting. So let's go back. I wonder if that's because it's got too many values. Okay, so what I did, I was trying to generate too many values. I was trying to go between -5 and 5 in increments of a quarter, and it just didn't cope with calculating that many values. Now that I have done that, I've just taken the step down to 0.5, and so what I can see that interests me is that the calculator literally says error when it can't generate a number, so that's good. So I was interested to see what was happening between -3 and -2. So I can tell you that -2.5 is -1.75. So that is in red, about there, and so as f of x approaches 0, so that means f of x is very small, so I'm looking at the values between, the x values between -3 and 1, the f of x values are negative. The reciprocal will not change that. 1 divided by a negative number will still be negative. So what I'll end up with is a shape which will look like this. So I've got my asymptotes. It's a more rounded shape. It doesn't look quite like a parabola, but that's one section of my graph. If I have a look at what's on the other side, around the -5, and my calculator did handle doing 1 divided by f of x. So where I had -5 for an x value, I had f of x is 12, so g of x is 1/12, which is not very big at all. As f of x approaches infinity, 1 on f of x approaches 0. So here we're already down to pretty much the limit of what I can manage to do as far as graphing. So -4, when x was -4, f of x was 5, so 1 on f of x is 1/5, which is still, you know, pretty small, but slightly more. What's going to happen on the other side? So what we've got here is these values. This is going to be our y equals 0, being an asymptote. That didn't go well at the end, but you get the idea. And because of the symmetricality of our original function, okay, so bad things happened there. Let's just ignore that. And we've got the same thing happening on the other side. So the values I got were, you know, not terribly useful to sketch, but they are what they are, and that's what happens with reciprocal functions. All right, so the red gives me the reciprocal function. Try not to have them as wobbly as I do. Stick the arrows on. All right, so what I'm going to do is I'm going to end this recording here in case something's gone wrong, and that way I don't have to redo it. So I'll do the next example as a separate recording.